All right, let's talk about section 1.3. We're going to continue the review of Algebra 1 topics that we should already be familiar with, but we're going to change gears a little bit. We talked about closure and addition and subtraction addition and multiplication properties last time in 1.2. We're going to change gears and talk about square roots. It'll be a two-part video lesson. In the first part, we're going to try to demonstrate how we can estimate non-perfect square roots using perfect square roots. That'll be a small portion of the lesson, not really something that's very critical in my opinion. But the ability to multiply and divide square roots is very critical, and we want to be able to write square roots in the simplest form and be able to simplify them. So, to get started, we need to talk about what a square root is. Let's look for a minute at the symbols that we're going to use, what we call different things, and then we're going to talk about this concept of a principal root. If we look at this check mark looking symbol, we should all realize that means take the square root. It means square root. It has a name though. That symbol is called a radical, and then any number or expression inside the radical is what we're going to call, like this 16 here, is a radicand. Just some naming conventions here. Nothing to get too worked up about. The key element here is, if I asked 99% of the people what the square root of 16 is, I would get the relatively quick answer that the square root of 16 equals 4. You would be correct. This is what the square root of 16 equals. But if you think about it for a minute, some people might think, well, what about, a square root is a number that I multiply by itself to get this number. What if I did negative 4 times negative 4? That would also give me positive 16. And while that is a true statement, the concept of a principal root, we're going to restrict radicals to only principal roots, and principal roots are only the positive version that we have. So we'll get back into the negative versions when we start talking about solving for variables, like solve for x squared. But for now, and for any time we have a square root symbol that is used, we are only concerned with the positive or the principal root. So the square root of 25 is simply 5. And the square root of 36 is simply 6. It is the positive version only. Now it is possible to get a negative value. If I wanted the negative root, I would just put negative square root of 9 equals negative 3. But I would have to put this negative out in front. If I don't put the negative in front of the radical, it's always going to be a positive result, okay? Principal roots just means the positive root, folks. All right, now let's talk about estimating non-perfect squares. Well, we all know what the square root of 16 is, I hope. And we also all know what the square root of 25 is. But what about the square root of 20? Well, 16 is smaller than 20, so the square root of 16 should be smaller than the square root of 20. And 25 is greater than 20, so the square root of 25 should be greater than the square root of 20, or the square root of 20 should be less than the square root of 25. So if I wanted to estimate the square root of 20, I could get 4 is less than the square root of 20, which is less than 5. So the square root of 20 falls somewhere between 4 and 5. And in some of your books, it probably goes in a little more detail that wants you to estimate to the nearest tenth, but we're not going to concern ourselves with that. As long as you realize that you could find a general value for the square root of a number by looking at the two perfect squares surrounding it, that's good enough. So if we had, let's say, the square root of 43, what's the square root, perfect square one below? Well, it would be the square root of 36, and one above would be the square root of 49. So we know that 6 is less than the square root of 43, and that is less than 7. So the square root of 43 is somewhere between 6 and 7. All right, now we get into the meat and potatoes of this lesson, multiplying and dividing square roots. All right, when we try to multiply and divide square roots, first we're going to do some multiplying. The book will call this the the property, the multiplication property of square roots, or the product property of square roots. So we can look at the product property for square roots. I'm going to use some perfect squares to demonstrate this. If I have the square root of 9 times the square root of 4. Let's step down right here. We know what the square root of 9 is. It's 3. And we know what the square root of 4 is. Well, that's 2. 3 times 2 equals 6. That's nice. When we followed our order of operations, we should always evaluate square roots first, and then we should do the multiplication process. But let's say that we wanted to do the multiplication of the two radicals first. Could we do it? It turns out we can. Anytime I multiply two radicals together, I could just write one big radical and multiply the radicands underneath it. 9 times 4. Here's the radicand is 9, here the radicand is 4, and I'm multiplying these two roots together. I could rewrite it as the square root of 9 times 4. 9 times 4 is 36, and the square root of 36 is 6. So my two answers are the same. So how does this help me out, you may be wondering? Why don't I just take the square root of each thing and then multiply them? That works out great, as long as they are perfect squares. And I recommend that if it is a perfect square, evaluate the square root first and then do your multiplication. But let's say we find ourselves in a situation where we're trying to multiply the square root of 5 times the square root of 20. In this situation, 5 is not a perfect square. 20 is not a perfect square. So the only way to multiply these two things together is to combine them under one radical. We still multiply 5 times 20. And 5 times 20, and you know, back here your head may be spinning a little bit. How am I going to do this problem? Square root of 5 times the square root of 20. We can do the estimation process. We can go through and figure out a whole bunch of approximations. Just take a deep breath. Write one big radical, 5 times 20. That equals the square root of 100. Hey, that looks a little nicer, doesn't it? What's the square root of 100? It is 10. So a seemingly difficult problem is made much easier by using the product property of square roots. Okay, I told you we were going to talk about multiplying and dividing. A product has to do with multiplication. Let's talk about division here, the quotient property of square roots. Now, just like a radical times a radical, I could write one big radical and do the multiplication. If I have, instead, the square root of 16 divided by the square root of 4. If I have a radical over a radical, I could rewrite this division problem, this quotient, with one big radical and keep the radicands underneath it, just divide them underneath. So here I'm just saying, instead of the square root of 16 divided by the square root of 4, I'm going to do the square root of 16 divided by 4. First, let's try to work this out. Step down a level. The square root of 16 equals 4, and the square root of 4 equals 2. So if I do this right, my final answer should be 2. So let's go back up. We'll use the quotient property instead of simplifying first. The square root of 16 over 4. Well, 16 divided by 4 is 4. So what's the square root of 4? 2. Look at that. That works as well. Okay, let's try that with a problem that is not perfect squares. Let's take a look at the square root of 125 over the square root of 5. Now 125 is not a perfect square and 5 is not a perfect square. But I can rewrite this problem with one big radical, the square root of 125 over 5. The square root of 125 over 5 equals the square root of 125 divided by 5 is 25. So my answer here is simply the principal root only, 5. I can use the quotient and the product properties of square roots to combine different radicals, different square root problems, in ways that makes it easier, that will make it easier to simplify them and come to a final answer. Now let's look at simplifying square roots. And when I talk about simplifying square roots, we all know if it's a perfect square, we just evaluate it. So if I had, let's say, the square root of 4, well, 4 is a perfect square, so we can just jump outside this radical symbol, and it equals 2. It just, I guess you can jump out this way, huh? He just jumps outside of it, and he equals 2. The radical symbol's gone because we've already evaluated the square root of 4. It is 2. But let's say we have something like the square root of 48. Not a perfect square. But when I simplify my square roots, I want to identify all of the perfect square factors of a number and take them out. What do I mean by perfect square factors? Well, I could rewrite the square root of 48 as a product of two numbers. I could write it as the square root of 24 and 2, I agree, but 24 is not a perfect square either, so that doesn't help me out. What about 16 times 3? Hey, that works. Now, I have a product here, 16 times 3. If you remember my product property of square roots, I can kind of do it backwards now. I could rewrite this as the square root of 16 times the square root of 3. And when I do that, I can evaluate the square root of 16, which is 4, times the square root of 3. There's no more perfect squares that I could factor out in here, in 3, so I leave it like this. Here's my final answer. And it's okay to write it this way. It really means 4 times the square root of 3. I don't need to approximate. I don't need to use a decimal. I can just write it 4 times the square root of 3. And we can remember from our first couple lessons there that a non-perfect square is an irrational number. So I don't want to write the decimal out anyways for 3 because it goes on forever. This is a more exact answer. So you may be asking yourself, well, let's say we have a higher number like 128. You can see my little cheat sheet over here. Let's talk about the square root of 128. That's a big number. It's going to take me a while to go through and see if there is a perfect square factor in there. Well, one piece of advice is anytime we're dealing with manual calculations of these things, or even a calculator calculation, we need to identify all the possibilities and list them out in order. So go over to the side of the top of your paper and just write down 2, 3, 4, 5. Write down some numbers, like maybe up to 12 or 13. And right next to those numbers, write down their squares. So I could say that 2 squared is 4, and then we have 9, we have 16, 5 squared is 25, 6 gives me 36, 7's 49, 8's 64, 9's 81, 10's 100, then we got 121, 144, and then we have 169. All right. Now, when I'm looking at simplifying a single radical, like the square root of 128, I want to try to find perfect square factors inside of here. The first thing I do is divide 128 by 2. 128 divided by 2 gives me 64. So then I'm going to look at my perfect square list here, and I'm going to see, is 64 on it? Hey, 64 is on it. So that is a perfect square factor. I divided 128 by 2, and I got 64. So I could rewrite this as the square root of 64 times 2. And then I could split my two radicals, the square root of 64 times the square root of 2. And we know that the square root of 64 is 8. So my final answer is 8 root 2. And if you wanted to plug these in your calculator to check and verify, you'd find out that 8 times root 2 is the same thing as the square root of 128. Now let's talk about one that's not quite as nice though. Let's look at this one right here, 90. The square root of, I don't want to use green. We'll use blue. the square root of 90. So the first step, again, remember I said that, I'm going to use, I'm going to divide 90 into 2. 90 divided by 2 is 45. I'm going to come over and look for my perfect squares. Do I have a 45? I don't. I don't have a 45, but it gives me a starting point, somewhere I could use to jump off with. And I could use a calculator to help me out if I need to, but I could say, what's the first perfect square less than 45? What's 36? Well, if I typed in 90 divided by 36, that's not going to help me out. It's 2.5. Can't have any decimals. It's got to be a perfect factor, a whole number factor of 90. So what about the next one below 36? Then I go to 25. If I do 90 divided by 25, that doesn't work either. It gives me 3.6. Okay, let's step down again, and I have 16. I'm going to try that. 90 divided by 16, hey, that one didn't work either. I got 5.625. So now let's step down to 9. 90 divided by 9. Hopefully you guys realize that 9 is a perfect square factor of 90. I could rewrite this as the square root of 9 times the square root of 10. And the square root of 9 is 3. So my final answer is 3 root 10. I can always go back and double check. Is 10, or does 10 have any perfect square factors? So the factors of 10, we've got 1 and 10, 2 and 5. Those are all the whole number factors of 10, and none of those are perfect squares. So here is my final answer. And again, if we wanted to go in and try 75, let's look at the square root of 75. We could divide it by 2. What's 75 divided by 2 is 37.5. So I'm looking at 37 or lower. 36 is the first one. When I do 75 divided by 36, I get some crazy huge decimal. That's not a perfect whole number square factor. So if I look at the next perfect square down is 25, and 75 divided by 25 is 3. So I could rewrite this as the square root of 25 times the square root of 3. And we know the square root of 25 is 5 times root 3, because I still have my root 3 here. Here's my final answer. I can't simplify or pull out any more perfect square factors from 3, so I get 5 root 3. Alright, and we can go over this in class more, or watch this video again if you need to. The idea is that we're identifying any perfect square factors inside of these elements that we could pull out. Let me go back and point out one quick thing with a square root of 48. Let's say we're doing the square root of 48. And in your mind, you automatically think, well, 4 is a factor of 48, and that's a perfect square. So you want to just write down the square root of 4 times the square root of 12. That's totally fine. It's reasonable. Now we can rewrite this as the square root of 4 is 2 times root 12. But what we need to do at every step is make sure there are no more perfect square factors inside of your radical. So when I look at the square root of 12, are there any more perfect square factors? I've got 1 and 12, 2 and 6, none of those are perfect squares, 3 and 4, 3 and 4. So I could rewrite this again as 2 times the square root of 4 times the square root of 3. There was another perfect square in there, it was 4. And then when I take the square root of 4 and I bring it out front, I get 2. And I need to multiply it by the coefficient that's already out here. So I get 2 times the square root of 3, which is 4 root 3. And if we look back up to our earlier problem, we get the same answer. It just took an extra step. And that's okay, as long as you take that extra step to do it. Now, this section, I know we're getting a little long in the video, but this section is pretty straightforward. Like radical terms. It's kind of like terms. If I have like radicals, I can combine them. I can add them or subtract them. To multiply or divide them, I don't have to have like radical terms. I can go ahead and use the property, the product and quotient property of multiplication, or the product and quotient property of square roots to combine those elements and to simplify them rather. When I'm trying to use addition or subtraction, I have to have like radicals, just like I have to have like terms. We can't add 5x plus 3y. That's as simple as it gets. But if I had 5x plus 3x, that just equals 8x. Well, in this problem, it's 5 root 2 plus 3 root 2. Remember, we're saying 5 times root 2. So it's really like there are 5 root 2's here being added together, plus 3 root 2's being added together. My end result is going to be 8 root 2. As long as my radicals are the same, I can just add the coefficients. I can just add these two guys together. Just like 5x plus 3x equals 8x, 5 root 2 plus 3 root 2 equals 8 root 2. So what about this problem here? 5 root 3 minus root 12. Can I do the subtraction? Now, those of you who are astute are saying to yourself, no, we can't. We can't because they're not like radicals. Exactly, my radicands have to match. I have to have the same exact radical problem in order to do any addition or subtraction. But if you look a little bit closer, is this simplified first? It's not. So step one is always simplify your radicals. All right, simplify your square roots before moving forward. Remember, we can rewrite this as 5 root 3. There's no more perfect square factors in here. But what about root 12? Root 4 times root 3, right? So I could write it as 5 root 3 minus 2 root 3. And now I have like radicals. Root 3 here and a root 3 here. I just subtract my coefficients. And I get 3 root 3. All right, so like radicals, almost exactly like terms, I have to have the same radical in order to be able to add or subtract them. But we need to make sure that they are all simplified before we make that determination. So that takes care of the lesson. I'm going to work through a couple example problems now. I know we're a little bit over on time, but I feel like giving you guys a couple example problems. Feel free to watch or shut it off if you got it, however you guys choose to proceed. All right, let's look at the negative square root of 50. Again, when we're talking about the negative square root of 50, give myself a little room to work here. The negative square root of 50. The first thing I need to do is try to simplify this square root. So I need to pull out any perfect square factors. So I can come up here and I can write down my perfect square factors. I've got 4, 16, 25, 36, 49, 64, 81, 100, 121, 144. That's close enough for now. And I need to remember that this negative out front is going to stay there. I can't just disappear it, so it's always going to be negative. I could rewrite the square root of, or the negative square root of 50 as negative square root of 25 root 2. So I could simplify this. It is negative, look at me making mistakes here. What is the square root of 25? 5. And the root 2 has to stay there. Negative 5 root 2 is the simplified version of negative square root of 50. Now it's very important. This negative doesn't distribute. You don't distribute into the square roots. The negative stays outside the radical. You can't just jump inside a radical. So let's look at square root of 49 over the square root of 81. You guys want to hit pause and see if you can figure it out first, feel free. If we did the square root of 49 over the square root of 81, I can't do 49 divided by 81, but my quotient property of radicals allows me to split this up. I could write it as the square root of 49 over the square root of 81. Now I have two perfect squares, so I could write the square root of 49 as 7 and the square root of 81 as 9. And here's my simplified version. Let's look at the next one here. The square root of 96 over 6. Now, in order to solve this problem, I like blue. Let's use blue. Square root of 96 is not a perfect square. I could try to simplify this before I do the division problem. I could. And I would end up at the right answer. So let's work it both ways. A lot of times, though, if these two numbers can divide into a whole number, it's going to be nicer to work the problem through without simplifying the radicals first. So what's 96 divided by 6? Does it work? It does. In fact, 96 divided by 6 is 16. So I can rewrite this as the square root of 96 over 6, which equals, that's a little stray mark right there, the square root of 16. And that would just be 4. So let's say that we wanted to simplify the square roots. Let's say we didn't see that, and we ended up trying to simplify the square root of 96 first. We can't simplify the square root of 6. That's as small as it gets. But if I did the square root of 96, let's come back up to my list of roots over here. I have my perfect squares over here. Half of 96 is 48. So the first one below 48 is 36. So when I do 96 divided by 36, that's not a whole number, so we're not going to use that one. Go down to the next one, 96 over 25. We already know that's not going to work. What about 96 divided by 16? Hey, 96 divided by 16, that works. And I get 16 times 6. So I can do the square root of 16 times the square root of 6, still over the square root of 6. And when I do my simplification now, separate part of the problem here, the square root of 16 is 4, and the root 6 stays there, and I'm dividing it by root 6. So now my root 6's will cancel, and I'm left with 4. Either of those two processes are going to get you to the right answer. I would suggest that if you can do the division problem, this way is much quicker than going through and simplifying first. So always try to combine your radical terms before you simplify if you can, or try to do the multiplication rather and the division before you simplify if it's possible. Now let's look at this one. The square root of 80 minus 5 root 5. Okay, we can't do this because they're not like radical terms. But if we are going to be able to do it, we're going to have to write them both in terms of square root of 5. Now in this case, we have to try to simplify the square root of 80. If this is a square root of 5, we can go ahead and narrow our choices down right now. I need to be able to rewrite this as, if it's going to work, the square root of something times the square root of 5 minus 5 root 5. So let's see if 80 goes into 5 evenly. What's 80 divided by 5? It's 16. So the square root of 16 times the square root of 5 minus 5 root 5. And I could rewrite the square root of 16 as 4. So I'm left with 4 root 5 minus 5 root 5. And this combined together, 4 minus 5, is negative 1 root 5, or simply negative root 5. All right, folks. Give the concept checks a shot. We'll see you in class tomorrow.